So let's continue our analysis from last time. So last time we actually spent most of our effort learning how to solve the time-independent Schrödinger equation as the first key step in understanding the solutions to the time-dependent Schrödinger equation. We learned a number of general lessons that you can use to solve the time-independent Schrödinger equation in a wide variety of circumstances. And we also learned the particular solutions for the case that concerned us. Let's first go through those very general lessons that will help us for any type of a problem that we might face. The first thing is that we notice that our solutions exhibit different behavior in two very different types of regions. One that's called a classically allowed region, where the energy is greater than the potential, and the other behavior we see in so-called classically forbidden regions, where the energy is less than the potential. These are regions where a classical particle would have no possibility of being. Now, what we learned for the classically allowed region was that the wave function tends always to curve toward the axis, which then towards the x-axis. That then results in oscillatory behavior characterized by a local wave vector k, which has the formula that I've given to you here. If we are in the happy circumstance where the potential is actually constant, which would make this k a constant, then it's very easy and quick to write down the most general possible solution for such a region. In that case, the wave function then becomes simply a combination of sines and cosines with appropriate prefactors, which is exactly equivalent to having two adjustable parameters multiplying not sines and cosines, but actually complex exponentials, which then represent a forward traveling wave and a backward traveling wave. Whichever of these two forms we use are mathematically equivalent, but depending upon context, one is generally much more convenient than the other. In particular, when we're trying to solve for these parameters, as we saw last time, the algebra usually works out very nicely if we pick appropriate sines and cosines. On the other hand, as we'll see today, this complex exponential form is very useful when we are trying to understand the behavior of the solutions that we are finding, because we know this represents particles traveling to the right with momentum h bar k, whereas this piece represents particles traveling to the left with momentum h bar times k. If we turn now to the forbidden regions, where the energy is less than the potential, these solutions always curve away from the axis. That corresponds then to exponential behavior, characterized by an exponential constant, a local constant which would take on the following form. And if we are again in the happy circumstance where the potential happens to be constant in that given region, the most general possible solutions then come as exponential solutions, which we can write in a very parallel form as to what we had above, where we simply have hyperbolic cosines and hyperbolic sines with prefactors in front. These are arbitrary prefactors that can have any adjustable value. I just like to write this as I times b for reasons that may become clear in a future lecture. Of course, we could use the cosine sine form paralleling what we have in the allowed regions. We can also use the exponential forms, which would then be a decaying or a growing exponential, again with two undetermined parameters. Once again, the choice of which form to use depends upon context. When we are trying to solve for these coefficients, it turns out that much like the sine and cosine case, the hyperbolic sine and cosine are most convenient when trying to solve for the coefficients. On the other hand, when we are trying to understand the behavior of our solutions, whether or not, for instance, they are allowed solutions or not, whether it's exponentially growing or shrinking, becomes very important. And so this form becomes very useful. We then learn that in addition to these generic behaviors, there are a series of boundary conditions that we can use. And these are critical because if we look at the general solutions that we've written down, they have these undetermined parameters. And what determines the values of those parameters primarily are these so-called conditions or boundary conditions. We learned three different types of boundary conditions, which are enough really to solve almost all problems. There are just two other boundary conditions that we will learn about in later lectures, but the primary boundary conditions are first, that we can never be in a situation where our wave function, as we head out towards infinite distance from our system, approaches either plus or minus infinity. As we saw, our wave function then just wouldn't be normalizable, and even worse, it would correspond to the particle being located at the edge of the universe, not a particle that would correspond to the experiment that we are doing. We also learned that the wave function and its first derivative must always be continuous everywhere, and in particular, it's very useful for matching these different coefficients and generating equations which we can solve to apply those adjunctions between the different types of regions. And these will be continuous, we proved, if the potential is always finite, even if there is a discontinuity in the potential. As long as it stays finite, we have these two continuity conditions on our wave function. Finally, we learned that if we have any extended region of space where the potential is infinite, that would mean we, of course, are in a classically forbidden region because the potential is so high. There would be these very rapidly exponentially decaying solutions as we go into that region, and then what we end up with finding is that the wave function is exactly zero over any extended region where the potential might be going to infinity. The one proviso I'd like to put in for you guys is that if we happen to have an infinite potential at a single point, namely a Dirac delta function, we're going to get a different type of boundary condition. And that's one of the two final boundary conditions that we will have in order to complete this set. But as I've said, what we have so far is enough to solve most problems that you may face in the near future. Now, we can turn then to the results we had in our particular case. Our particular case, we were interested ultimately in what happens if I take a wave packet consisting of particles that primarily have a certain kinetic energy E, right? That would be the total energy of my particles, and then I send them in towards a step in the potential, where the potential has this discontinuous change, or really, it's continuous at some very fine, say, Planck scale, but at our scales it looks discontinuous, where it switches to a value of V0 very suddenly at the position x equals 0. This immediately divided our system into a classically allowed region and a forbidden region, which I called region 1 and 2 respectively. In region 1, we had worked out the corresponding wave vector using the fact that the potential is 0 and our generic formula. And similarly, we worked out the exponential decay constant for region 2, given the height of our potential and our energy. And then finally, we used the boundary conditions to solve for every bit of the wave function except for this one constant that comes out in front. This is, of course, at the end of the day, this is related to the normalization of our wave function. It'll turn out the details of that we don't have to make a specific choice for this quite yet, as you will see. We can work it into another piece of our problem later on. But it's important to remember that it's just related to the normalization of our function. And then we have our solution in two different regions. In the allowed region, x less than 0. It turned out to be sines and cosines with the prefactors that I've solved for here. This is for always applies this piece when x is less than 0. When x is greater than 0, we then had a decaying exponential with this particular prefactor. And finally, I'd like to point out, if you're interested in the value at x equals 0, because our wave function is always continuous, these two functions must actually match, so it doesn't matter which function you use when you evaluate at x equals 0. So I'll just arbitrarily pick this one and use this solution for x greater than or equal to 0. Here then is a sketch of the function that we had found. In the forbidden region, it is just a pure decaying exponential. This is characteristic of an evanescent wave. And I just wanted to point out that it has a certain exponential decay length, which of course is related to the inverse of the exponential constant alpha 2. That's how far in typically we could find a particle. I'd like you to notice that there actually is non-zero probability of finding a particle in this forbidden region when we look at it quantum mechanically. It's just that probability decays very rapidly with distance, and the characteristic decay scale, again, is just 1 over alpha 2. In the allowed region, I just have my standard sinusoidal behavior. Out here, I have what's called a standing wave. And in fact, if you look at the wavelength out here, if you want to work that out, that corresponds, of course, to then just 2 pi over k1. So we can characterize either an exponential decay length or the wavelength of the corresponding behaviors in each of the two different regions. So that then made up a complete solution to our time-independent Schrodinger equation. The last thing I'd like to do before we really proceed is to remind ourselves of what the big picture is. What is it that we were planning on doing with the solution? Well, all of that came back to our plan to solve the time-dependent Schrodinger equation, which you may remember involves this quantum principle of superposition and a three-step approach. In the first step, we need to first solve the time-independent Schrodinger equation in order to solve for the states that appear in our superposition. The next step, which we are about to embark upon, is to write down this superposition and to pick the weights that go in the superposition. And then finally, step 3, today we will be able to begin to analyze our results, our predictions for this situation. Now, in terms of the superposition, just a quick reminder, it's a sum over some label, and that what we sum over is the weights associated with each value of our label. Those we will pick in a moment to match our boundary conditions, to match the initial condition. Then we have our states, which are the solutions to the time-independent Schrodinger equation. And finally, we attach these so-called dates, right? These pieces that give us the time evolution. And finally, just review as we begin to work on this. Here is the expectations that we've been having. We know that if I plot the position of a classical particle versus time, when this classical particle comes in and hits this potential step, it doesn't have enough energy to go into the forbidden region, so it is immediately reflected back with the same velocity. So we expect a trajectory like this, where the particle just hits that interface at x equals 0. And we've timed things so that will occur at time t equals 0, and then it is just reflected back. What we're expecting quantum mechanically, and now we're beginning to see the first inklings of this. Quantum mechanically, what we are expecting is that this particle can actually be found in that forbidden region. So we're expecting the trajectory of a wave packet to actually be able to go past this classically forbidden and enter the classically forbidden region. It will pass that interface. By the correspondence principle, though, we expect it will ultimately be rejected from that region. So it's going to have to turn around in there somehow and then be ejected back into the classically allowed region, where we expect it to continue on its normal trajectory, which will then be a backwards motion with the same energy with which we came in. So we expect to come out with a trace that has the same slope or velocity of our classical expectation. But the key signature that something interesting has happened, that we've actually entered the forbidden region, a phenomenon known as quantum tunneling, is that there is going to be a delay in the time at which this packet comes back out, and that delay time, delta t, is something that ultimately we want to understand. And I'd like to just foreshadow for you a little bit. You might want to think about what might determine how long we actually spend in there. There is actually enough information on this slide for you to make a good order of magnitude estimate for exactly how long we should be spending in here. And I'll let you all ponder that for a little bit while we begin our analysis for today, and we're going to pick up here on step 2, writing down the superposition and picking the weights.